Welcome to the class of electrochemistry. In our last lecture, we started discussing this electrolytic cell. Now, if we recall this slide, so this is a Daniell cell in normal case, but if the applied potential difference is greater than 1.1, that means if this one is biased in reverse sense, then what will happen that the reverse reaction will take place, that copper will dissolve and copper 0 to copper sulphate, and zinc metal, I mean zinc 2 plus ion will return to zinc metal. Okay. So, basically electrolysis will take place. Now, normal this natural direction of the reaction is this, and in that case delta G is negative, but if you make if you make this delta G in the reverse sense negative, that you apply a reverse potential drop against this electrode, so that here this reverse reaction will take place. Now, typically what is the difference between, in that case it will be an electrolytic cell where electrolysis will take place. Now, what is the difference between a galvanic cell and an electrolytic cell? So, electrons are, so galvanic cell and electrolytic cells. So, here in galvanic cell, electrons are generated at the anode, electrons are generated at the anode, and they are consumed at the cathode, and naturally they will it will be consumed at the cathode, means in the other electrode, that is which is plus. And in electrolytic cell, electrons come from an external power source. That is why I was telling that if you supply an external current such that the cell is reverse biased. Okay. So, which supplies to the cathode, electron is supplied to the cathode and removes them from the anode, that is cathode, in that case it is minus. Cathode in this case is minus, anode is in this case is plus. So, you are supplying electron from outside to the cathode. Okay. So, typically this is the difference, that the electrons are generated from within the cell as a result of some chemical transformation. Here electrons are supplied from outside, that is the electrons are fed from outside to this cell, and the chemical reaction is taking place over there. Okay. As for example, in case of electrolytic cell, the classic example will be electrolysis of molten alkali halide. So, in it is, so electrolysis of molten alkali halides, like say sodium chloride, it is in molten state. Okay. So, it is the method of industrial method for preparation of sodium metal. Okay. Now, so what happens for in this case? So, at cathode, so reactions are taking place both at the anode and cathode. So, therefore, cathode reaction it is reduction that gets you in a liquid, and corresponding potential is equal to minus 2.71 volt. Anode reaction is Cl minus gets you half Cl2 in gas form plus electron, and corresponding potential is equal to minus 1.36 volt. That gets you as a total of 4 for the net reaction. Net reaction is sodium plus Cl minus, giving rise to Na0 in liquid form plus half Cl2 in gas form. So, therefore, the net E for this process is E0 for this process is minus 4.1 volt. Okay. Now, so it is in molten state. Remember, this is in molten salt. It is not an aqueous solution. Okay. Now, think about another example where you are using this aqueous solution of some salt, like say for example, aqueous solution of say nickel chloride. So, in that case, one thing that you should remember, that here when you do the electrolysis, you need to have you need to use inert electrodes. So, in this case carbon electrodes are generally used. So, carbon electrodes are generally used for the electrolysis of a molten sodium chloride. Next is for aqueous solution of nickel chloride. In this case, platinum electrodes are used. So, if platinum electrodes are used, this cathode reaction is like nickel 2 plus twice electron, that is reduction, that gets you nickel 0 solid, and corresponding E naught is equal to minus 0.24 volt. Anode is 2 Cl minus that gets you Cl2 gas plus twice electron. E naught is equal to minus 1.36 volt. So, net reaction is nickel 2 plus 2 Cl minus gets you nickel solid plus 2 nickel solid plus Cl2 gas, and the net E0 is equal to 1.6 with a negative value 1.6 volt. Okay. Next is electrolysis of say aqueous solution. Aqueous solution means it is a aqueous solution of something, okay, some electrolyte. So, in case of electrolysis, I mean when you talk about electrolysis of water, then what is happening at anode? Electrolysis of water. Okay. So, anode reaction, H2O that gets you half O2 gas plus twice H plus twice electron, where E naught is equal to minus 1.23 volt. Cathode reaction is 2H2O plus twice electron gets you H2 gas plus 2OH minus E naught is equal to minus 0.83 volt. So, these are the things that happen. So, there will be a competition between the above reactions, I mean these reactions, above mentioned these reactions, and I mean this reaction will be there. Say for example, there may be a competition between above reaction means this reaction with this reaction, or there may be suppose in place of nickel something else is dissolved. So, possibility is also there. I mean, the competition between this reaction and the reaction involving the electrolyte that is dissolved in water, that is there. Now, the question is, why do we need to dissolve an electrolyte in water? Because pure water, for pure water, its resistance is very high. Okay. So, therefore, electricity will face a huge resistance to when it is passing through just pure water. So, therefore, in order to reduce that, you need to add some electrolyte, so that the electricity can pass through and the required reaction may take place. Okay. Now, say for example, suppose you have say sodium chloride. Okay. So, aqueous sodium chloride, what is going to happen? Suppose you have aqueous sodium chloride. So, aqueous solution of NaCl. Okay. So, what is going to happen? So, cathode reaction, cathode means reduction, cathode reaction will be, the favored reaction will be like 2H2O plus twice electron, giving you H2 gas plus 2 OH minus, where this potential will be like potential will be like E is equal to 0.41 volt when the concentration of OH minus is around 10 to the power minus 7 molar. Otherwise, it would have been like this. And anode reaction will be chloride minus plus water, that gets you half Cl2 plus electron. In this case, your E naught is minus 0.95 volt. Okay. So, therefore, see, you have a competition over here. Okay. You have a competition over here that this is one reaction, anode reaction, and there could be another anode reaction as a whole. So, therefore, in this case you see that it is less negative than this one. So, this reaction is expected to be favored over this one. And also there is another reaction what you can think of in the cathode case, that cathode reaction could be like reduction of sodium plus electron, that gets you sodium liquid, but its potential is E naught is minus 2.7 volt. Okay. So, therefore, this is much larger in negative sense. So, therefore, this reaction will not be favored, but this reaction will be followed. So, therefore, net reaction will be Cl minus plus water, that gets you 2H2 gas or H2 gas plus half Cl2 plus 2 OH minus. Okay. So, you can appropriately balance it, that is not a problem anyway. So, in this side you have 2 OH minus. Okay. So, therefore, so basically you have 3 H2, right, here 3 H2. Okay. Anyway, so you can balance it appropriately. So, in this case this E is minus 0.95 volt. Anyway, these numbers are not that important, but anyway, I just wanted to tell you that when there is a competition, then you need to consider these numbers. Okay. So, that will decide which one will be favored over the other. Okay. So, for electrolysis of pure water, as I mentioned to you, that it has got high resistance. So, therefore, it is difficult to undergo electrolysis. So, electrolysis of water pure water, high resistance, So, that means difficult to undergo electrolysis. Okay. So, in that case little bit of acid, if you add little bit of acid, then it becomes conducting and then reaction is taking place. Okay. So, if you add little bit of acid, then cathode reaction may be if you use a platinum pair of platinum electrodes, then cathode reaction will be 2 H2 plus twice electron, that gets you H2 gas plus 2 OH minus E naught is equal to minus 0.83 volt. Anode reaction is water to get you half O2 gas plus 2 H plus twice electron, and here E naught is equal to minus 1.23 volt. So, net reaction is 3 water liquid, that gets you H2 gas, that gets you H2 gas plus half O2 plus other, okay, and net E naught is equal to minus 2.06 volt. Okay. Next, we will move on to one important thing which are basically laws of electrolysis. It is called the Faraday's Faraday's law of electrolysis. It is by Michael Faraday. In 1832. Okay. So, laws are like this. First law of electrolysis, the weight of substance formed at the electrode. So, law 1, Faraday's law number 1. So, weight of substance formed at the electrode, weight of substance means the substance which is formed out of this electrolysis, substance formed at the electrode during electrolysis is directly proportional to the quantity of electricity that passes through the electrolyte, through a pair of electrodes. So, mass is proportional to Q, or you can write mass is equal to Z into Q, where Z is the electrochemical equivalence. Okay, what is electrochemical equivalence? So, when Q is equal to 1, then M is equal to Z. So, when 1 coulomb of electricity has been passed through the electrolyte, then whatever mass of the concerned electrolyte, I mean concerned material has has been formed at the electrode is called the electrochemical equivalence of that particular material. Number 2, that is law number 2, the weight of different substances, weight of different substances, substances means this electroactive substances formed by the passage of same quantity of electricity are proportional to the equivalent weight of each substance. That means your W1 by W2, M1 by M2, W or mass whatever is equal to U1 by E2, or which is equal to, you can write, since Q is equal to IT, you can write Z1 I T divided by Z2 I T is equal to E1 by E2, or you can write Z1 by Z2 is equal to U1 by E2. That is, ratio of the electrochemical equivalence equal to ratio of the chemical equivalence. Okay. Now let us focus our attention again back to some industrial process. Industrial process means electrolysis of brine solution. Brine means sodium chloride solution. Okay. So, in this case, anode reaction, we can write two anode reactions like 2 Cl minus giving rise to Cl2 gas plus twice electron, its corresponding E naught is equal to minus 1.36 volt, and 4 OH minus O2 gas plus 2 water plus 4 electron. Here E naught is equal to minus 0.4 volt. Okay. So, thermodynamically this reaction should be favored, but the point is that this is very slow, kinetically very slow. So, therefore, if it is slow, then it is a problem, but at the same time the other reaction is kinetically fast. So, therefore, what will happen, that this reaction will be, this reaction will be prominent. Okay. So, therefore, this reaction, although this is thermodynamically favored, but kinetically this is slow, therefore, kinetics will take over thermodynamics. So, kinetically controlled, as a kinetically controlled product, this one will be measured. So, this reaction will take place. So and for the cathode reaction, it is again two reactions, Na plus electron, that gets to Na liquid. It is E naught is equal to minus 2.7 volt, an anode reaction, it is water plus twice electron, that gets you H2 gas plus 2 OH minus, where E naught is plus 0.41 volt. So, therefore, this reaction will be favored over the other reaction. So, net reaction will be your NaCl plus water giving rise to NaOH at the cathode plus H2 gas, that is also at the cathode, and plus Cl2 gas at the anode. Okay. So, this way you know what is happening, that you put brine solution in, and basically the diagram looks like this. You have a sodium ion selective membrane over here, it looks like this. So, H2 is coming out here, chlorine, it is coming out, this is minus, this is plus. Okay. So, there this basically you are doing electrolysis over here. It is not, it is basically you are supplying this current from outside. Okay. So, therefore, these two are cathode reactions. Okay. So, therefore, what is happening, that you have sodium hydroxide coming out and water is put in here, sodium chloride is fed, and here spent brine is taken out. Okay. So, this is an sodium ion selective membrane, Na plus selective membrane, and sodium ion will move this direction, Na plus will move this direction. So, this is precisely what is happening when electrolysis is carried out on the brine solution. Okay. So, what can be the other application of electrolysis? Other application of electrolysis can be electrolytic refining of some metals, impure metals. So, you can refine, like suppose you have say for example, 2 silver electrodes. Okay. So, one is say the one which is at the anode is say for example, it is impure, and the other one in the cathode is a pure form. So, what will happen when you electrolyze it, then the impure silver will be dissolving, and the pure silver will be deposited to the other. In this way, you can purify this impure metal to pure metal. So, another application can be electrolytic refining of aluminum. Next is storage battery, I mean storage like primary storage battery or primary storage cell, or secondary storage cell. Okay. So, the thing is that this one is capable of being recharged, okay. And electrode reaction can proceed in both either direction. I mean whether it is it is a electrolysis or maybe normal electricity production. So, during charging the electrical work is done on the cell. So, when you charge it, electrical work done on the cell, and as a result of which the free energy required to force the reaction. So, this will provide the free energy, the free energy to force the reaction in the backward or in the reverse direction. Okay. Now, in case of primary storage cell, see ordinary flashlight cells or battery, ordinary flashlight battery, okay, cannot be recharged with efficiency. You cannot recharge, cannot be recharged. It is not better to recharge this, because maybe some accident can take place, because it is designed to I mean designed in such a way that you will get electricity once, okay, in a single use, but you cannot reuse it by charging it like a secondary cell. Okay. And the amount of energy it can deliver, the amount of electrical energy that it can deliver will depend on the amount of chemical substance that is there while it is manufactured. Once that stored chemical is exhausted, the battery life is gone or battery dies. Okay. So, these are the typical differences between a secondary storage cell and a primary storage cell, that you can store electricity, but the point is that you cannot store electricity for infinite period of time, but it is some finite period for some finite period of time. Now, let us turn our attention to the secondary storage cell. Secondary storage cell is a lead acid storage cell, lead acid storage cell, lead acid storage cell. It is Gaston Plante. It is done by Gaston Plante in 1859. Okay. The cell is like this: Pb solid, PbSO4, then H2SO4. That is why it is lead acid, aqueous, then PbSO4, then PbO2, so that is this. So, net cell reaction is Pb plus PbO2 plus 2H2SO4 aqueous, that gets you 2 PbSO4 plus 2H2. So, when the discharge is taking place, that is you take out electricity out of it, this is the normal direction of the reaction. When you charge it, then the reaction has been driven in the backward direction. So, it is charging and the other one is discharging. Okay. So, and what happens that after it is discharged, you see that some amount of water is generated. So, generally density of sulfuric acid H2SO4 rho H2SO4 is approximately twice rho water. So, when discharge is taking place, your this sulfuric acid solution, which is the electrolyte of this active electrolyte of this cell, it is diluted. Okay. So, generally concentration of H2SO4 that is used in this secondary storage cell, it is about 6 mole per decimeter cube. Okay. And normal cell voltage is about 2.1 volt at 298 Kelvin. Okay. Now, what are the problems with this lead acid cell? Problem could be, so problems may be like its weight is high. So, weight is a problem, because you need to have this large amount of lead involved over there along with sulfuric acid. So, weight is a problem. So, during winter time the viscosity of sulfuric acid increases during winter, and as a result of which flow of ions from one plate to another, it becomes sluggish, and as a result of which that reduces the current. So, reduces current. That is why there may be problem during winter time, starting of car, there may be some problem happens when during winter time. And also, since it has some internal resistance, so slowly it may discharge. Now, number 4 could be if it is charged very fast. So, for fast charging, so H2 evolution is so much that it will happen on the, the bubbles of H2 will be there on the lead surface, and so therefore, lead when coated with lead oxide that forms one electrode. So, lead oxide will be removed from lead, and as a result of which the electrode is modified. So, ultimately it will damage the cell. So, typical diagram is like this: series of electrodes are there, and one is inserted in between the other. So, this is your plus PB cathode, this is PB cathode plate with PbO2 coating, and this is basically your PB anode plate, and the whole thing is immersed in sulfuric acid, H2SO4 with given specification. Okay, so that is an example of a storage battery. Next we will come to dry cell. It is Leclance's dry cell. Leclance's dry cell. It is in it was invented in 1866. Okay, so basically the electrode reactions are like this. At anode you have zinc 2 plus twice electron, okay, and you have a carbon cathode with a brass cap. That is, perhaps you have seen in the market that this AA battery or AAA battery. So, the technology is like this. So, you have a zinc cup or zinc container, and you have this like one cover, and then you have this carbon electrode, and you have on top of this there is a metal cap. So, that connects, I mean that makes the electrical connection. Okay. So, so you have here paste of NH4Cl, and you have MnO2 over there, and MnO2 manganese dioxide is also there. So, carbon cathode reaction is 2 MnO2 plus 2 H plus, that is coming from ammonium ion, okay, plus twice electron, that gets so Mn2O3 plus H2O. Okay. So, or if you write in the form of NH4Cl then or NH4 plus, then you should have written NH3 over here, like if it is, if you replace this with NH4 plus, then 2 NH4 plus, then you will have to write plus 2 NH3. Okay. So, therefore, it has a limited shelf life due to self discharge, because it has got some internal resistance through which this electricity is discharged. So, voltage is 1.5 volt, and the cell reaction we can write like this: zinc plus 2 MnO2 solid plus 2 NH4Cl aqueous, that gets you zinc chloride plus Mn2O3 solid plus 2 NH3 plus water. Or it may proceed further as follows, or I mean beyond this it may happen. This reaction may proceed further as follows, zinc solid plus 2 MnO2 solid plus 2 NH4Cl aqueous plus 2 H2O liquid, that gets you zinc chloride plus MnOH whole 2 solid plus 2 NH3 gas. Okay. So, this is the typical reaction, and it is marketed like giving an outside jacket with some some material, maybe some plastic or some other material, paper packaging may be there. So, this is the oldest version of this dry cell, that is known as Leclanche's cell. Now, modern version of alkali cell, modern version of alkali or this type of cell, modern version of this primary storage, it is invented in 1949, that KOH has been used. KOH has been used in place of this ammonium chloride, which is basically corrosive to this zinc metal, this one is corrosive to zinc metal. So, here what is happening, you use KOH and zinc powder, and it gets a higher current gets higher current rating and voltage is about 1.5 to 1.65, okay, and the net reaction can be zinc plus 2 MnO2, that gets you zinc oxide plus Mn2O3. So, this is called the alkaline cell, which is the modern version of this Leclance's cell. Okay. So, so this is basically that completes our discussion with respect to this dry cell and this or the primary storage and the secondary storage. So, this completes your discussion about primary or secondary storage. Okay. So, while summing up, so what we have learned in this particular piece of lecture, that is, we started our discussion with difference between basic difference between this galvanic cell and electrolytic cell. In one case we are getting electricity out of it, that is chemical energy has been converted to the electrical energy. In this case you apply electricity from outside, so that the natural reaction, in some cases you may require to reverse the direction of the natural reaction. Okay. So, if you bias the cell in appropriate fashion, then the natural direction of the reaction will be reversed, and as a result of which electrolysis may take place. So, as an application, I mean as an example, as examples of electrolysis, we discussed this molten salt electrolysis or maybe electrolysis of aqueous solution of different electrolytes, and also we discussed if there are a number of competing reactions, then which reaction will predominate over the other, and that is decided by the value of the potential, that is value of the potential means the magnitude of the potential, and also the in some cases the kinetics of the process, or maybe in some cases thermodynamics of the process is also important. Next we talked about this Faraday's law of electrolysis. There are two laws. So, we discussed these laws, and then we moved our attention to, we talked about this primary storage and secondary storage. As example of primary storage, we talked about this Leclance's cell and lead acid cell as example of the secondary storage. So, this completes I mean today's discussion on on electrochemistry. So, in next day, I mean next class, we will take up this fuel cell, that is an important concept. So, we will take up the basic idea of fuel cell, and then we will move on to this another important issue, which is called corrosion. So, till then, thank you.